where we left off in the last video. I think we were getting a reasonably good appreciation for how huge the sun is, especially relative to the Earth, and how far the Earth is away from the sun. That most of these diagrams that we see when we in science textbooks, they don't give justice. In fact, when I showed it this sun over here that was about 5 or 6 inches across, I said Earth would be just this little speck about 40 feet. It wouldn't be this distance, it would be about 40 feet to the left or the right, or it would have a radius, its orbit would have a radius of about 40 feet. So it'd be this, you wouldn't even notice it if you were looking at this thing over here. It would be this little speck orbiting at this huge, huge distance. If you look at this sun over here, if I were to draw the whole sun, it looks like it would have a diameter of about 20 inches. So in this situation, this Earth right here, and this is drawn to scale, this Earth would not be anywhere near this close. It would be about 200 feet that way, or about 60 or 70 meters, 60 meters. So you could imagine if the sun was this size, sitting on something like a football field, this little speck of an Earth, this little thing right here, would be sitting on the other 40-yard line, 60 meters away. So huge, you wouldn't even notice it. You might notice this from a distance, but you wouldn't even see this thing over here. And the other planets are even further. Well, not all of the other planets. Obviously, you have Mercury. You have Mercury here. I think most of us are familiar with these, but I'll just list them here just in case. That's Mercury. This is Venus. Mercury is the smallest of the planets where it's not debated whether it's a planet. Pluto is the smallest, but some people debate whether it's really a planet or kind of just a large solar body or a dwarf planet or any of those type of things. But then you have Venus, probably the closest in size to the Earth, or it is the closest in size to the Earth. And then you have Mars, and then you have Jupiter. And just to give a sense of, once again, how far these things are, if I were to go back to the analogy of this being the size of the sun, then Jupiter is 5 times further than Earth. So this would be, if I were to actually do this, the scale distance, this would be 300 meters away. 300 meters. So if I had a nice big, maybe medicine ball size sun right over here, maybe basketball size sun, a little bit bigger than a basketball, this looks on my screen, then I would put this little thing that's smaller than a ping pong ball, I would put this 3 football fields away. That's how far Jupiter is. And then Saturn's about twice as far as that. Saturn is about 9 times the distance. So let me make it clear. The Earth is 1 astronomical unit away from the sun, roughly. Its distance changes. It's not a perfectly circular orbit. Jupiter is approximately a little bit 5 plus astronomical units, so a little bit more than 5 times the distance of the sun to the Earth. And Saturn is approximately 9 astronomical units, or 9 times the distance from the sun to the Earth. So once again, this would be 9 football fields away. Or another way to think about it would be essentially a kilometer away. If we had a kind of a medicine ball sized sun, this little smaller than a ping pong balled Saturn would be a kilometer away. And I just want to really reiterate that, because you never kind of visualize it that way. Because just for the sake of being able to draw it on a page, you see diagrams that look like this, and they really don't give you a sense of how small these planets are relative to the sun, and especially relative to their distance from the sun. And then after Saturn, you have Uranus, and then Neptune, and then Neptune. And obviously, these guys are even further. And just to give you a sense, it's very easy to start talking about galaxies and universes and all of or the universe. But I really just want to get, already what we're talking about huge distances, huge scale. We already talked about that it would take a jet plane 17 years to travel from the Earth to the sun. Multiply that by 5, about 100 years to go from Jupiter to the sun. 200 years to go from Saturn to the sun. So you could have had Abraham Lincoln get into a jet plane, and he still wouldn't have gotten, if he left from Saturn, he still would not have gotten to the sun. So these are huge, huge distances. But we're not done with the solar system there, just to give a sense of scale. So this right here, that's the sun. And each of these planets are actually narrower than these orbits. So they just draw these orbits here, but you wouldn't actually even see the actual planets here at this type of a scale. But this is 1 astronomical unit right over here, the distance from the sun to the Earth. Then you have Mars. Then you have the asteroid belt. There you have the asteroid belt. Asteroid belt, which also has some pretty big things in it itself. And it has these things that are kind of considered almost dwarf planets, things like Ceres. You could look those type things up. And then you have Jupiter out here. And once again, we said it would take 100 years, or roughly 100 years, for a jet plane to get from Jupiter to the sun. But even if you take this whole box here, which is a huge amount of distance, of roughly about 5 astronomical units, it would take about 40 minutes for light to get from the sun to Jupiter. So this is a huge, huge distance. But even this huge distance, we can put it into this little box right over here. This little box right over here. So this whole box right over there can be fit into this box. And that you need to do that in order to appreciate the orbits of the outer planets. And so on this scale, the Earth and Venus and Mercury and Mars, their orbits look pretty much, you can't even differentiate them from the sun. They look so close. They almost look like they're part of the sun when you look at it on this scale. And then you have the outer planets, Saturn, Uranus, Neptune. And then we have a Kuiper belt. And this is more asteroids, but these are kind of more frozen. And when you think of ice, you always think of water ice. But out here, it's so cold, and it's relatively getting dark now because we're pretty far from the sun, that things that we normally associate as gases are going to be in their solid form out here. So this isn't just rocky elements. This will also be things that we normally associate as gases, like methane, frozen methane. But even here, we're not done. We're not even out of the solar system yet. We're not even out of the solar system yet. And actually, just to give you a sense of the scale we're operating right here, I have this chart right here from the Voyager mission. So the Voyager missions, Voyager 1 and 2, actually Voyager 2 left a little bit earlier, a month earlier. Voyager 1 is just traveling faster. They left about a year after I was born. A year after I was born. And their current velocity, just to give you a sense of how fast, Voyager 1 right here. Voyager 1 right here is right now traveling at 61,000 kilometers per hour. That's about 17 kilometers per second. The size of a city every second. It's going that fast. That's, at least in my mind, an unfathomably fast velocity. This thing has been traveling roughly that fast. It's been going around planets and gaining acceleration as it went around orbits. But for most of the time, it's been going at a pretty fast speed. And just to translate it to people who don't relate to kilometers, that's about 38,000 miles per hour. So this huge, huge, unfathomably fast speed. And it's been doing it since 1977. I was learning to walk, and when I was learning to walk, it was traveling at this super fast speed. And then when I was learning to talk, I mean, our whole lives, when we're sleeping, everything we're eating, I'm in elementary school, it's still rocketing out of the solar system at roughly this speed. Its velocity has changed, but especially once it got outside of the planets, it's been roughly at this velocity. So it's just been rocketing out. And I don't want to say only, but it's gotten this far. It's gotten about, if we look at it on this scale, it's gotten about that far right there. It's about 115, 116 astronomical units. And to give a sense, so there's two ways to think about it. One says, like, wow, that's really far. Because we know that even on this scale, you can't even see Earth's orbit. So this looks like it's a pretty far distance. And just to give you a sense of how far 116 astronomical units are, if 2,000 years ago, Jesus got on a plane, I actually cut and pasted a copy of Jesus just for visualization purposes. But if he got on a jetliner at 1,000 kilometers per hour and went straight in that direction, in the direction that Voyager would only just now be catching up to Jesus. So this is a huge, 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 huge distance. But at the same time, even though it's a huge distance, especially relative to everything else we've talked about, relative to just even the outer reaches of the solar system, we're still talking in terms of a small scale. So that's how far Voyager is. And just to give a sense, on this scale, so this whole box over here, can be contained in this box. And when you look at this box, Voyager's only gotten about that far after traveling at this unbelievable velocity for over 30 years, for about 33 years. And just to give you an idea of these other things, Sedna right here is one of the, it's a it's a reasonably large-sized outer solar system object. It's one of the furthest objects that we know of in the solar system, and it has this very eccentric orbit. So it gets, I don't want to say relatively close, but not unreasonably far away, and then it gets really far away from the sun. But even Sedna's orbit. So if I were to look at this, so this whole box over here, can be contained right over here. So in this diagram right here, you wouldn't even be able to see. It would be like a speck how far Voyager has traveled in 33 years at 38,000 miles per hour. You would not even be able to notice. You wouldn't even notice that distance. And even though you can't even notice that distance, we still have the sun's influence. The the gravitational pull is still attracting things to it. And this right here, we speculate that there's the Oort cloud, and this is where the comets originate from. And this is just a bunch of frozen, you can almost, frozen gases and ice particles and things like that. But this is kind of, we're starting to get to the outer reaches of the solar system. And this distance right here is about 50,000 astronomical units. 50,000 astronomical units. And just to give a scale, because you hear a lot about light years and all of that, light years are about 63,000 astronomical units. So if you go a light year out from the cloud, a light year out from the sun, you'll end up in the Oort cloud, the hypothesized Oort cloud. And just to give a sense, another scale, the Oort cloud is actually, most of the planets' orbits are roughly in the same plane. But this right here is the orbit of the planets. And once again, these lines are drawn too thick. They're just drawn the thinnest possible so that you can see them, but they're still drawn too thick. And this gets us all the way to the Kuiper belt. But all of this over here, so all the way out to the Kuiper belt, all the way out to all of the major planets. This is Pluto's orbit right over here. This is Pluto's orbit right over here. This whole diagram is only sitting in right over there. You can barely see it. This whole diagram is just that dot in this. And then you can see the Oort cloud all around it. It's more of a spherical cloud. And we think it exists. Obviously, it's hard to observe things at that distance. So hopefully that gives you a beginning sense of the scale of the solar system. And what's really going to blow your mind, if this hasn't blown your mind already, is that this whole thing's going to start looking like a speck when you even just look at the local area around our galaxy, much less the galaxy as a whole, much less the universe as a whole. Anyway, I don't want to get, well, anyway, this is starting to get crazy.